Hi, I'm An Jian from Simon Fraser University. Here I'm going to present our work, Guarantee Safe Approximate Reachability via State-Dependency-Based Decomposition. This is the joint work with my supervisor, Professor Mo Chen. In this video, we'll talk about 4 parts: introduction, the method, simulation results, and finally give conclusion and future work. At first, we'll introduce Hamilton-Jacobi reachability in robotic safety analysis and its current computational challenge as curse of dimensionality. Autonomous systems are becoming popular in our life. For example, we have autonomous car which can sense the environment and drive in the city. However, we often hear the news about a drone crash or accidents from autonomous car, indicating that safety is still an important issue remaining to be solved, especially for safe-critical systems, where the failure or collisions will result in serious injury to people, to the robot itself, and the environment. We need a formal method to verify the safety. Hamilton-Jacobi reachability is such a formal method. For example, imagine we are riding a bike. Following the physics rules, we use differential equations to describe the dynamics, where x, y as position, v as speed, and psi as orientation. We also consider the uncertainties in the world. For example, wind may blow the bike to somewhere else. We model the wind as the disturbances added to the dynamics as dx and dy. Thus, when you ride this bike and suddenly you find out there's a tree in front of you, because of the momentum of the bike, you have to steer away early enough to avoid collision. Thus, in reachability, we focus on computing backward reachable tubes, BRT, as states from which reaching the unsafe states is inevitable. And in the picture, it is the unsafe area that the bike has to avoid. The biggest challenge for HJ reachability lies in the computation and space complexity. Given the system dynamics, to obtain a reachable tube, one needs to solve the HJ-PDE using dynamic programming on the grid. For example, for previous Dubin's car model, we will generate 3D grids for the state space and solve PDE. According to the plot, this method scales badly with respect to the state dimension. Currently, system above 4D has been considered intractable, which might still be a naive model for the control of autonomous vehicles. In the next part, we'll briefly introduce previous methods and then propose our novel decomposition method that helps alleviate the curse of dimensionality. For a ground robot like this, we can use the 3-dimensional model to describe its dynamics, which you can directly control speed. Or you can use a higher dimensional model that you control the acceleration instead of speed. We argue that this 4D model will better guarantee safety because it is closer to the realistic scenario. However, it is slower to solve. Thus, dimension reduction is crucial for safety verification of robots because it can make high-dimensional model computationally tractable. Previously, there are different types of dimension reduction techniques. Projection-based methods first project the 4-dimensional reachable tubes into low-dimension subspace and solve them. This method is extremely flexible for dimension reduction and can scale to high-dimensional systems. However, it introduces large conservatism in the approximation. On the other side, the system decomposition method can offer an exact solution of reachable tubes without any conservatism. However, it only works on a certain class of dynamic systems, thus it's restrictive. So is there a way to balance these two aspects that largely reduce dimension but don't introduce much conservatism? The answer is yes, via our state-dependency-based decomposition. For example, let's look at 4D quadruple integrator. We use the state dependency graph to represent the system dynamics, where each node represents a state, and if Z1's derivative depends on another state Z2, we have a direct edge in the graph between Z1 and Z2. Then, based on the state dependency graph, we can decompose a full system into 3 chain subsystems that are connected subgraphs. Since we don't know the grid value for the missing states here in light blue, we assume they are worst-case disturbances to guarantee the conservative solution. Alternatively, you can decompose into 2 3D systems. Therefore, it is very easy to choose either decomposition choice, which is to choose high-accuracy solution or quick solution based on computation resource available. After this decomposition, there might be some missing states in a subsystem that doesn't have a grid. For example, in S1, we have Z3 as missing states. In this case, we'll look at the concurrently computed BRT from chain subsystem S2. So when solving Z1, Z2 equals to AB, we fix Z2 as B. Thus, in the BRT from subsystem S2, we'll have the range R for Z3 inside its own BRT. To guarantee the conservative computation of BRT in subsystem S1, we can choose Z3 from R under the worst case. In addition, because we don't choose the worst case from the whole computation range, the BRT in S1 won't be too conservative. Here are more decomposition cases using our methods. Given the dynamics, we can easily draw the state dependency graph and break it into several subsystems. We show that our method is pretty flexible with a large variety of system dynamics where there are integrators involved. Computation space and complexity can be saved while conservatism is properly preserved. Next, in simulation, we compare our approximation results to the ground truth. We also show our results for 60 bicycle, which is previously considered intractable. We show the results of 4D integrator. Here we decompose a 4D system into 3 2D systems. The ground truth is to solve 4-dimension system in 4D grid, and the approximation is solved on 3 2D grids. Here we show the 3D slice of 4D BRT. First, we show our solution is an over-approximation. Because BRT are unsafe area, thus to avoid over-approximation is guaranteed to be safe. At the same time, we see that our approximation doesn't introduce much conservatism. In terms of computation time, we are 200 times faster than ground truth. We then investigate the 60 bicycle system, which is a popular model for ground robot, but it was too complex to solve previously to the best of our knowledge. Based on the graph, we decompose it into 6 subsystems. Here are the results of 3D slicing X, Y, and Z dimension. The red cylinder is the target we want to avoid, and the green part is the BRT. We show that safe trajectory starts from outside of the green BRT and successfully avoid the red target in 2 seconds. Unsafe trajectory starts from inside the BRT and inevitably collide. Thus, staying outside of our approximate BRT guarantees safety. Finally, we make conclusion and future work. In this paper, we propose a novel decomposition method that largely alleviates the computation complexity for approximating BRTs without introducing much conservatism. We also provide a simple way of making trade-offs between computation space, speed, and the performances. There are several limitations of our work, which are also our future work. First, our method only works in collision avoidance scenarios, because over-approximation of BRT can be obtained with projection. Under-approximation techniques will be really helpful for goal-reaching cases. Second, For now, human effort is still needed to decompose the graph. We hope to automate this process using graph search techniques. Finally, target set is required in subsystems to find range of missing states. Thus, we should think more carefully about the target set design. Finally, I want to thank my supervisor, Professor Mo Chen, for all the guidance and endless support on this project. Thank you, and I'm happy to take any questions.